Hello and welcome. Here's a tip. If you're interviewing to be a waiter and they ask you, why would you make a good waiter? You can just say, because I'd bring a lot to the table. In this video, we're going to learn about the integral test for series. Let's get started. We'll start by looking at the series 1 over n and compare it with the integral from 1 to infinity of 1 over x. In this first picture, we're looking at, in figure 1, the graph of 1 over x. And what we've done is we've drawn dots that represent the terms of the 1 over n series. Remember that the series is like, so the 1 over n is like the 1 over x function, but it's only the dots that happen at n equals 1, n equals 2, n equals 3, or in other words, at x equals 1, and x equals 2, x equals 3. So it's just picking out the dots of the 1 over x curve at 1, 2, 3, 4, and so on. Now what we've done in the picture is drawn a rectangle based on each of these dots. The height of the rectangle is the y value of the dot. The width of the rectangle is going to be 1 in every case. When we do that, the area of each of these rectangles are giving you the terms of the 1 over n series. So you're going to get an area of 1 for the first rectangle. Now in figure 1, the y coordinate, or the y scale, is stretched a little bit compared to the x scale. So this is really supposed to be a square, but we're just exaggerating the y scale a little bit. So it's 1 times 1, which is 1. For the next rectangle, we've got 1/2 times 1, which is a half. And then 1/3 times 1, which is a third, and so on. So the heights of each of these dots are the same thing as the areas of each of these rectangles. Now if we add up the areas of all these rectangles, that's a representation for the series 1 over n. That's another way of representing that in a visual way, representing the series 1 over n. So it's 1 plus a half plus a third plus a fourth, and so on to infinity. Well, let's take a look at the integral from 1 to infinity of 1 over x. So figure 2 is showing us that. Here's the curve 1 over x. The integral from 1 to infinity of 1 over x is just the area under that 1 over x curve from 1 to infinity. That's what that picture looks like. Let's put the two side by side. So we have figure 1 on the left, we have figure 2 on the right. We have the graphical representation of the series on the left, and the graphical representation of the integral 1 over x on the right. We'll notice that the series has all these rectangles that are above the curve, and so that's going to lead to more area in that calculation. So this series, if it converges to something, is going to be greater than the integral from 1 to infinity of 1 over x. So by comparison, we can say that since the integral from 1 to infinity of 1 over x dx, does that one converge or does that diverge? If you said it diverges, then that would be correct. And that's because this is a p of 1. And when p is less than or equal to 1, for 1 over x to the p, then your integral, your improper integral, is going to diverge. So if that integral diverges, if the area under the integral is diverging, if it's infinite area underneath this integral, well then the series is going to have to diverge as well, because look at the picture, it has even more area. So the series has to diverge because there's more area when you visualize the series in that way. Now let's look at the series 1 over n squared and compare it to the integral from 1 to infinity of 1 over x squared. In figure 3, we're looking at the 1 over x squared curve. And now, instead of drawing our rectangles to the right of each of the dots, we're going to draw them to the left of each dot. So on that first interval from 0 to 1, we're going to make our first rectangle, and we're going to use the height of the function at x equals 1 to determine the height of that rectangle. So we're going to have this height of 1, and then the width is 1. For the next dot, we're going to draw a rectangle to the left, and that is going to give you a rectangle that, well, if we plug in the 2, we'll have 1 over 2 squared, which is 1/4. That's going to have a height of 1/4 and a width of 1. So when you compute the areas for these, you're going to get 1 over 2 squared, which is 1/4, 1 over 3 squared, which is 1/9, then 1/16, then 1 over 25, and so on. Basically, you're getting the series 1 over n squared if you add up the areas of all those rectangles. So this is a visualization for the series 1 over n squared. Let's take a look at the integral of 1 over x squared. So here's 1 over x squared in figure 4, and the integral of 1 over x squared from 1 to infinity is going to be the area under this curve. So it's the area under this 1 over x squared curve from 1 to infinity. Putting the two side by side, we have figure 3 on the left, figure 4 on the right. Notice that the area under this series here, the area under this series, is going to be smaller because the rectangles are under the curve. It's going to be smaller than the area from 1 to infinity of 1 over x squared, except there's this extra rectangle that doesn't quite fit with the integral of 1 over x squared. But if we added that extra rectangle of area in to the integral, then definitely the integral plus that extra rectangle from 0 to 1, plus that extra rectangle, which is actually a square, just stretched, would definitely have larger area than all of these rectangles that we get from the series. So writing that as an inequality, if you take the integral of 1 over x squared and you add in that extra rectangle, so plus 1, that's going to give you greater area than the area of the series, just visually speaking. So then by comparison, because the integral from 1 to infinity of 1 over x squared, what does it do? Converge or diverge? You said converge, that's correct, or it converges. That's because p is 2, which is greater than 1. Then the smaller series is also going to have to converge. You know, if this integral of 1 over x squared converges, it'll converge to something. When you add 1 to that, that number is going to be bigger than the number that the series 1 over n squared is going to represent. So by comparison of the series to the integral, we can figure out that since the integral converges, the smaller series has to converge as well. It's kind of like the comparison test for integrals, but here we're comparing an integral to a series by just looking at it in terms of areas. So putting this together, we have the integral test, which connects series with integrals. It says that suppose we have the terms of our series, a sub n, are equal to f of n, where f of x is some continuous positive and decreasing function for all x that's greater than or equal to some positive integer big N. Then the result is that the series from n equals big N to infinity of a sub n and the integral from big N to infinity of f of x dx are both going to converge or diverge together. The two are linked together. And the link that between them is that a sub n is equal to f of n. Now, a couple of notes about the integral test. One is that the function has to be continuous. The reason is the function has to be continuous so that you can actually evaluate this integral. If it weren't continuous, you wouldn't be able to evaluate this integral. The function also has to be positive and decreasing for this argument to work. If the function falls below the x-axis, well then you're going to have net negative areas, and it's kind of hard to figure out what's going on with those negative areas. Our argument really only worked because our pictures were above the x-axis. So positive and decreasing as well. Decreasing to make sure that eventually the argument is also going to work. If it doesn't, then your area, the rectangles, would have to be shifted left or right based on when it's increasing or when it's decreasing. So this is the integral test, and again, it connects the convergence or divergence of a series with the convergence or divergence of an integral. How we're going to use it is we're going to ask, does this series converge or diverge? And to answer that, we're going to instead look at, does the improper integral converge or diverge? And if the improper integral converges, then the series converges. If the improper integral diverges, then the series diverges. So that's how we're going to use the integral test. We'll do an example in the next video. Thanks for watching, and see you in the next one.